Hello everyone, this is Mingchao, and this is my final project demonstration video. My project is Power Amplifier Linearization using DPD. My student number is D18124387, and my supervisor is Dr. Saleh. I'm going to introduce the background here. So, in the modern communication system, the signal power attenuation is inevitable in signal transmission. To make sure the output signal power meets the lowest output power specification, the power amplifier is always used in the signal transmission system. Due to the power amplifier is not a linear component, the non-linearity leads to the output signal distortion, which can degrade the communication system performance. To compensate the distortion caused by the non-linearity characteristic of the power amplifier, numbers of compensation approaches are developed. Digital predistortion is one of the most common used methods nowadays. The objective of this project is to simulate a power amplifier in MATLAB first, and then simulate DPD, apply DPD to the power amplifier, at last verify the performance of system with and without DPD. Here, I'm going to introduce some principal theory of the project. Due to the physical change of the power amplifier operation environment, for example, temperature, humidity, the power amplifier transfer function becomes to a time-dependent function, and this phenomenon is called power amplifier memory effect. Power amplifier model with memory effect is used in the simulation when the memory effect is considered. Memoryless power amplifier model means the transfer function of the power amplifier is not time-dependent. In this project, the impact of the memory effect is not considered. Only the memoryless power amplifier model is used. Then it's Saleh power amplifier model. This model is a typical memoryless power amplifier model, and the formula is simple by comparing with the other typical memoryless model such as Garbani model. In the formula of the Saleh model, R represents the input signal power magnitude, alpha and beta are the coefficients, and the typical value of these coefficients are shown in this slide. In this project, Saleh model is used to describe the behavior of the power amplifier. Power amplifier AM characteristic indicates the difference between the input signal power magnitude and the output signal power magnitude. And AM-PM characteristic represents the relationship between the input signal power magnitude and the output phase shift. Due to the non-linearity of the both AM and AM-PM characteristic, the output signal of the power amplifier will suffer the undesired impact of distortion. Digital predistortion. In this slide, the DPD block diagram is shown in the right-hand side of the slide. DPD can get rid of the undesired non-linearity impact by compensating the AM-AM and AM-PM distortion. A predistortor is located before the power amplifier, and the predistortor has the inverse linearity characteristic with the power amplifier. The adjacent channel ratio is always used to describe the linearity performance of the amplifiers. ACPR is also the ratio between the power of the main channel and the power of the adjacent channel. The simulation procedure. First, we are going to simulate the Saleh power amplifier model in the MATLAB. Then generate LTE signal by LTE toolbox as an input signal of the simulation. Then simulate DPD. Finally, combine DPD and the power amplifier together. Compare the output signal spectrum before and after DPD being applied. In this slide, the simulation block diagram is shown in the right-hand side. The input signal magnitude and the phase are extracted at first, and then the magnitude of the signal is input to the AM-AM and AM-PM program blocks in MATLAB to look up the corresponding output magnitude and the phase shift. Finally, we recover the signal by its phase and magnitude component to get the output signal. From this slide, I'm going to introduce some important results of the project. So the first one is the AM/AM and AM/PM characteristic of the power amplifier and the predistortor. The predistortor characteristic is inverse to power amplifier characteristic. The comparison between the original signal and the output signal with and without DPD is shown in this slide. The blue curve represents the original signal, the green curve represents the output signal with DPD, and the red curve represents the output signal without DPD. The ACPR value of the red curve is about minus 36.49, and the ACPR of the green curve here is about minus 24.67. So the difference between them is about 12 dB. And that is the improvement of the ACPR. I also set 2 verification experiments to verify the performance of the DPD system. Both verification experiments are coming from the paper on IEEE. The first verification experiment involves the 1-carrier WCDMA signal. So from the table, we can see the ACPR before and after DPD applied is about 20 decibel. The verification results meet the expectation on its original paper. Another verification experiment involves 1.4 kHz LTE signal input. Results of this experiment meet the expectation on its original paper. 2 verification experiments prove the current DPD system works properly. And by applying DPD to the system with 10 MHz LTE signal input, 12 decibel improvement is achieved on ACPR. But there are still some undesired distortion at the adjacent channel. Most undesired distortion are caused by the AM/PM characteristic, since the AM/PM distortion cannot be perfectly compensated by the distorter due to the different input signal power magnitude between power amplifier and predistorter. So an improved design block diagram is shown in this slide. In the improved design, the power amplifier output signal is feeding back to the AM/PM block of the predistorter to check the corresponding output signal phase shift value. So let's see the result. In the improved DPD system performance, the distortion at the adjacent channel is near 0. And in the old system DPD performance, the distortion at the adjacent channel still exists. And the distortion also decreases at the rest of channels by comparing with the old DPD system performance. In conclusion, 2 DPD designs are implemented in this project. 2 verifications and a simulation with 10 MHz LTE input signal are finished in this project. Both DPD designs compensated the distortion properly. The improvement in the first DPD is about 12 decibel. The improved DPD system compensates all the distortions at the adjacent channel, which is about 15 decibel. The project helps me to build a comprehensive and coherent understanding to the digital predistortion, and helps me to understand the significance of the power amplifier linearization to the modern communication system. Here, I'm going to demonstrate the implementation of the simulation project. Basically, we separate the simulation project into 4 different function scripts. So they are power amplifier and the predistortor simulation, the signal generate, input signal to the power amplifier, and then input signal to the power amplifier with DPD. So in the first script, we solve the characteristic of the power amplifier here by simply put the equation into the MATLAB. And then for the predistortor, we solve the second order equation here And this second order equation represents the characteristic of the predistortion, and it's derived from the power amplifier, because the characteristic of the predistortion is the inverse function with the power amplifier characteristic. And then we use the LTE toolbox to generate the signal. The configuration number is R13. We also need to sampling the signal before we input it to the power amplifier. So here we use the resample function to sampling the signal. And then we extract the magnitude component and the phase component of the signal. In this script, the signal is input to the power amplifier. The distortions caused by the power amplifier are simulated by two function blocks. In the first function blocks, the AM distortion is simulated. First, we input the signal magnitude to the power amplifier, and then we looking up the corresponding output magnitude value by the given input. The lookup table is built by the integral function in the MATLAB. This function allows us to use the appropriate parameters to build the lookup table. In the second function block, we calculated the output phase shift value. The approach we used in these two blocks are the same. The only difference is the parameter we used. In the second block, we used AM/PM parameter here. And in the first block, we used AM/AM. After we calculated the output magnitude and the output phase shift value, we need to recover the output signal. So first, we calculate the angle of the output signal by adding up the original test phase and the phase shift from the previous block. And then we calculate the imaginary part and the real part of the signal by multiplying the magnitude of the output signal with the sine function and the cosine function. And then we calculate the summation of the real part and the imaginary part to get the signal output. In the previous script, the behavior of the power amplifier is simulated by two function blocks. And in this script, the behavior of the predistortion with power amplifier are simulated by four function blocks. The difference between the function block of the predistortion and the power amplifier is the parameter we used. In the predistortion function blocks, we use the predistortion parameter. In the power amplifier function block, we use the power amplifier parameter to help us to build the lookup table. After we looking up the corresponding output value by using the lookup table, we recover the signal in the same way. And then we convert the signal from the time domain to the frequency domain, and then normalize the signal, which can help us to observe the signal spectrum easier. Thank you.